let's go ahead and get these notes done and complete it. That way you have your notes done. And there's no excuse that it did not get completed. So let's go to the velocity versus time graphs. It says here, though, in a velocity versus time graph, that we know that the time is on the x-axis and the velocity is on the y-axis. It also says here that the slope of the VT equals the acceleration of that object. So a VT graph tells me the acceleration of the object. Remember, we color-coded these VT graphs already. So when we see a flat horizontal line, it does not mean that the object's not moving, even though this should say velocity versus time graph. It doesn't represent a no motion occurring. It represents a constant speed is occurring. Now remember, mathematically, a constant speed or constant velocity is a zero acceleration, and that's the reason for it being a flat line. If I have a nice straight horizontal line, nice straight slope over here, my object is accelerating again, and then this inversely proportional line is a deceleration that's occurring, right? It's slowing down. Now let's go ahead and take a glance over here at our two graphs. It says with these two graphs, go ahead and calculate the acceleration. So if my acceleration, and I want to write that equation here, A equals VF minus VI over T. That's my equation. So over here, I need to find the VF, VI, and this is my velocity. So if this is my VI and this is my VF, here's my VF, here's my VI, and my T is how much time from here to here did it take. So my VF from my equation is 5. My VI is 5 over T, which is 10 seconds. 5 minus 5 is 0 over 10. I end up with the answer of 0 meters per second squared. Remember, over here we had a flat horizontal line. That flat line means that I have a constant speed. If I have a constant speed where I'm not speeding up or slowing down, I have 0 acceleration. Okay? That does not mean that my object's not moving. It is moving, but it's moving at a constant speed. Let's keep going. Let's go ahead and find the acceleration over here. I've got my initial velocity, my VI, I have my final velocity, my VF, and my T is right here. How much time did it take? So my equation is VF, and VF over here is, let's see, I'm going to go ahead and find a simple. I can use this one, but this one right here, this dot is right on the line, so I'm going to use that one, which is 30. My VI, this one's also right here on the line, which is 20. It doesn't matter. You can use this one. You can use this point and this point. You can use this point and this point. It doesn't matter which 2 points you use. Okay? Over the time, and since I use this one, I'm not going to use this time. I'm going to stop over here at 5 seconds. Now, 20 take away 5 is 10 over 5, which equals the answer of 10 divided by 5 is 2 meters per second squared. Okay, so there's our graph that we completed. Let's see where we fit, what we need to finish. We did our DT and VT color coding graphs. We did our kinematic equations. And then we have a few practice kinematic problems and some graphing over here. So let's go ahead and work on that some more. So let's look. Let's start off with these kinematic practice problems over here, and then we can move on to that last page, which is the graphing as well. I just want to do some practice problems with you first. because they might be a little difficult. I just want to make sure that we're all practicing. So let's start off with over here. Marissa Carr accelerates at a rate of, here's my acceleration. How long does it take for Marissa's, question mark T, car to accelerate from a speed of VI to a speed of VF? Okay, so I'm going to go ahead and write my variables VF, VI, D, and T. There are my variables. A is 2.6, VF is 9.65, VI is 8.85. D was never given to me, so let's mark that out, and then T is my unknown. Using my dichotomous chart over here, I'm going to ask myself, wait a minute, did they give me just two variables, no direction? No. Two variables, direction? No. Did they give me some type of acceleration? Yes, they did. So the question is, was D ever talked about, used, or discussed? And I looked over here, I marked it out, so the answer is no. It tells me let's use this equation. A equals VF minus VI over T. Now, my chart is not perfect, so we want to double check. Was A given to me? Yes. Was VF given to me? Yes. Was VI given? Yes. And was T given to you? Unknown. Since I have all the variables except for one, I can go ahead and algebraically solve for this. But since I'm not looking for A, I'm going to put this into the triangle and rearrange it. And so to do that, I cover up the equal part, VF minus VI, T is at the bottom, it does not matter where, and then plug in A. What am I looking for? I'm looking for T. So my new equation is T equals VF minus VI over A. Now my algebra, or the majority of my algebra, is done and out of the way. Let's fill in the blanks. VF is 9.65, VI is 8.85, A is 2.60. Okay? So now at this point, go ahead and grab that calculator, and let's go ahead and see when you do the math. Let me grab my calculator. 8.65. We're going to subtract that by, double check me, make sure my math is good. 9.65 subtract by 8.85 comes out to 0.8 over 2.60 divided by 2.60 comes out to an answer of 0.307. I'm going to round that up to 0.31, and I'm looking for T, which is seconds. Alrighty, let's practice again. A car accelerates through 85-meter stretch. Here's my distance. And it reaches a velocity, so if it's going to reach that velocity, that's the VF. And now it took 6.2 seconds T to get done. I'm not sure what that W is, forgive me. What is the car's acceleration? Question mark A. Step number 1, let's write down our variables. A, VF, VI, D, and T. A is my unknown, T is 6.2, D is 85, and VF is 27, and VI was never given to me. Okay, let's go back to our dichotomous chart. And the first question is, was D ever used, talked about, discussed, or given in any way? Yes, it was given to me. Was T ever used, talked about, or discussed? Yes, it was given to me. The next question is, was VI given to you? If VI is given to you, that's the equation you're going to use. Okay? If VI is not given to you, so if no VI, but yes VF, remember you're going to use the same equation, except D equals VF times T. Instead of plus, we're going to go subtract 1/2 AT squared. It's the equation on the previous page, okay, in your notes. So VI was not given to me. It tells me to go to this equation right here. Let's try that one. D equals VF, multiply it by T, minus 1/2 AT squared. That's the equation I need to use. So in that case, before I get started, I want to check or X in question mark. So D, check. VF, check. T, check. 1/2, check. A, question mark, and T is a check. Now, algebraically, because I'm only missing one variable, then I should be able to go ahead and complete this. So let's do that. 85 equals 27, multiply it by 6.2 minus 0.5, we converted the 1/2 to a 0.5, multiply that by A is my unknown, 6.2 square. Okay, so let's go ahead and let's solve this. 6.2 squared is 38.44, so let's plug that in. 38.44. So now should look like this. 85. Let me go ahead and multiply those two numbers so I can simplify this equation a little bit more. 167.4 minus 0.5 A times 38.44. Here's where I'm at. Again, please excuse my dear Aunt Sally, is super, super important, okay? Now I want to go ahead and simplify this a little bit more, and to do that I'm going to say 85 equals 167.4 minus all of those variables are actually being multiplied together. So I'm going to go ahead and multiply the 38.44 times 0.5. If my math is off, hopefully you have your calculators out to double check me. If so, I apologize, I'm not here to correct it. Please let the whole class know if that's the case. But I got 19.22A. Okay, that A has to stay there because all three are being multiplied. Now I need to go ahead and I need to simplify again. I'm going to come over here to the next step. And this is adding 167.4. I'm going to subtract 167.4 to cancel on both sides. So in that case, if I have 85 subtract 167.4, I end up with a negative 82.4 equals negative 19.22A. Now I still need to get A by itself, so I'm going to divide this side by the negative 19.22 because I don't want to leave that negative with the A. Cancel, divide, negative 19.22. So let's go ahead and do that. Double check my math, please. And when you divide a negative by a negative, hopefully you got a positive of A equals 4 point, and I'm going to round up to 29 meters per second square. Driving forward. So this math is completely doable. It just takes a few steps to get to it. Again, please excuse my dear Aunt Sally. It's super important in physics to follow the orders of operations, okay? Now you've got number 5 and number 6, and you have to try some of this on your own. So please stop and try this on your own. I'm going to go ahead and turn the page because we have one more page left. And other than that, there's a few problems for you to do on your own that you need to complete. Let's go ahead and let's look at this. This is just checking out the difference between and connecting dt versus vt. We did it on 2 different pages. Here it is on one page. What does a dt graph look like when it's stopped versus a vt graph look like when it's stopped? So on here, if it's a dt graph, it can be above the x-axis, it could be on the x-axis, or it could be below the x-axis if it is stopped. Okay? Now, that's an object that has a zero slope and there is no motion going on. It is completely stopped. But on a VT graph, remember, if it's stopped, it can only be stopped on the actual x-axis. Okay, both objects here, whether it's DT or VT, have a horizontal line, but on a VT, it's only going to be on the x-axis only. Okay? And on a DT, the flat horizontal line is going to stop wherever the object stopped at. Let's look at the next one. Constant velocity. Constant velocity, it's going to be a horizontal nice slope, okay? A horizontal nice looking slope is what it's going to look like. And again, we can have it above or below the x-axis depending on where is it going, towards the origin or away from the origin. All of those count, and all of those are taken into account whenever we're doing this and looking at this. So let me go ahead and draw those in. It could be like this for a DT, or it could look like this. Okay? If it's a constant speed on a VT graph, it is going to be a flat horizontal, and it could be above or below the x-axis, okay? But it's going to be a flat horizontal line. So let me zoom out a little bit. Constant velocity is a slope on a DT, and this one for VT has no slope. Now, if it's speeding up, it's going to have those curves. Do we remember? It's going to have those curves. It's going to look like that, or it's going to look like that. If it's speeding up on a VT graph, it's going to have a slope like this, or a slope like this. Again, though, depending on whether or not it's going towards the origin or away from the origin. Okay? So at the actual curve shows me acceleration is going on. This one, acceleration, is a nice straight slope. Directly relationship or an inverse relationship. And then the last one, slowing down or decelerating. On a DT graph, it looks like this or like this. Again, though, it matters on whether or not you're moving away or towards the origin. Over here, though, it's going to look like this, or it's going to look like this. There are no curves on a VT graph. There are curves on a DT, but not a VT graph. Just as a reminder, so just putting together what we did on those other 2 pages that we color-coded, just here so we can look and compare the differences between the DT and VT graphs. Other than that, all of our notes are done and completed. There's a couple of practice problems here, and then there's a couple of practice problems, I think. Here's one, and I think we have these over here for you to do as well. Okay, so please take a glance at these. Let's get those done. Oh, it looks like there's another one over here. Okay, the majority, or just about all of our notes are done. I need you to ask me questions from your notes when I get back, and let me know if you still have questions. Okay, have a good day. Bye-bye.